All right, today is Thursday, April 11th, 2024. It's my great pleasure to host this oral history interview on behalf of the Computer History Museum in Mountain View, California. My name is Bruno Marchon, and the topic of today's interview is the restoration of an IBM RAMAC. The RAMAC was the very first disk drive ever made. It was invented, fabricated, and commercialized in San Jose by a team of 50 or so IBM engineers in the mid-50s. It allowed for the first time real-time record transactions of large data sets that enabled computerized banking, airline reservation, inventory management, and many other applications. This RAMAC was a great commercial success for IBM, and it spurred a multi-billion-dollar hard disk drive industry that enabled today's internet and cloud storage. In 2001, Dr. Al Hoagland, then electrical engineering professor in Santa Clara University, and himself a former IBM RAMAC engineer, undertook an ambitious project to bring back to life one of the few still existing RAMACs. He lobbied IBM to procure one from their archives, and he put together a team of students and former IBM engineers to restore it back to working conditions. In the panel today are four of these people. Patrick Connolly, who was one of Dr. Hoagland's former students, and David Bennet, John Best, and Joe Feng, all IBM retirees and former engineers who dedicated a lot of their time to this project. Before we start the interview, I would like to acknowledge several people who were also involved in this project. The late Dr. Al Hoagland, of course, and some of his students, John Shepard, Andrew Giustini, Chris Hong, Egop Kozanian, Neil Rambia, David Nguyen, Viet Nguyen, and Jordan Villanueva. Of course, this would not have been possible without the support from Paul Lazevich from IBM Archives, who believed in this project and who was able to loan a RAMAC to Santa Clara University and eventually to the Computer History Museum. There were also key contributions from industry engineers and retirees, most but not all from IBM, and some who unfortunately are no longer with us. Jack Grogan, Mason Williams, Dick Oswald, Ed Thielen, Herky Hansen, Harry Kahn, Jack Harker, Grant Saviors, Lynn Lipchuls, Lou Taft, Gerardo Bertero, and Hong Sink Jung. And finally, of course, many thanks to Dag Spicer, senior curator here at the Computer History Museum, for his continued support and unequivocal interest to this great project. With this, gentlemen, welcome, and thank you for participating in this interview. We will start with each of you giving a bio, namely where you grew up, your hobbies, where you went to school, and your professional careers, and as well as how you got involved in this project. So let's start from the left. Patrick.
Okay, my name is Pat Connolly. Start at the beginning. I was born in Minnesota, then moved to Arizona very early, and my early childhood was all in the Phoenix area. Did a lot of robotics classes and events in high school, and then went to college at Santa Clara University, both for my bachelor and master's in mechanical engineering.
What was the topic in your master's?
My master's topic was control theory of multiple robots. So formation flying, essentially.
Mm-hmm. And when you were young, did you have any hobbies? Did you make little gizmos and toys?
Quite a few gizmos. I was the kid who took apart his dad's power tools.
Did you get your neighbors to come and help you fix and help them fix their tools and radios and such?
Not so much of that, but a lot of remote control cars, that kind of stuff.
Okay. And then we'll get back to you on how you got involved in this RAMAC project. Thank you. David, can you say a few words about where you were born, your education, and your career?
I was born and raised in Connecticut. My college degree is from Lafayette College in Easton, Pennsylvania. I have a BS in electrical engineering. I went to work for IBM on graduation in 1959. I started in Owego, New York, working on a project in the Federal Systems Division on the B-52 airplane. Transferred to IBM San Jose beginning in 1963. I was a product engineer through my career in IBM, and the product engineer is a person who's responsible for the design of a product which is in production or nearing production. And I had various ancillary, I guess is the word, assignments, but they were all kind of related to product engineering. I was a manager for a number of years, and I had a hobby within my assignment or close by. I'm interested in the history of technology, and I became kind of a self-appointed guardian, some say pseudo archivist for the historic collection that existed in San Jose, machines in the hallways, and then later on I got quite a bit of material from the publicity department, a lot of photographs and all, which ended up in IBM archives. I also have a hobby in I collect ancient cars. I'm a tinkerer, and I have very early cars, and so restoration was a familiar activity to me, and so I kind of gravitated into this one, working with Al Hoagland early on. Al took an interest in the collection that we had in San Jose.
Did the products you worked for in IBM all disk drives, or were you also connected to other technologies?
I worked in other storage. Well, I worked in storage devices, and then, but I was also a manager later on the 3800 IBM 3800 high-speed electrophotographic printer. So I worked on various other things, but storage was the main theme of most of it.
Okay, thanks, Dave. John?
So I'm John Best. I was born on Long Island. I grew up in Seattle. Moved to California when I went to college at Caltech. Got both BS and PhDs there. Left, and that was semiconductor-related work. And of course, you can never work on the same thing that you know something about when you go to work. So I left when I came to work at IBM. Right out of school, 1979, came to San Jose Research and immediately started working on magnetics. I worked on magnetic bubbles for a year and a half. Was getting worried that it wasn't going to go anywhere, so I switched over to working on hard drive kinds of things, and my manager then was Al Hoagland. So I've known him for a long time, since '81, and we kept in touch, which was part of how I got involved with this thing. Then worked on a variety of things in the hard disk drive area in IBM Research. Then got co-opted into doing management kinds of things and ran the IBM Almaden Research Lab for a while, and then development for our hard drive division, and then moved to Hitachi when IBM sold the hard drive division to Hitachi. Retired in early 2008, and that's about the time Al called me and asked if I wanted to work on this project. He and I had been keeping touch about this because I had an interest in RAMAC and history before that.
Thanks, John. Joe?
So I'm Joe Feng, and I was born in China and I was raised in the Chicago area. I went to Caltech as an undergraduate and as a graduate student as a physics major. So as a graduate student, I worked on nuclear particle accelerators to be used in semiconductor physics. And then I eventually got a job in IBM doing thin film magnetism. Started in Yorktown, moved to San Jose, where I was working on bubbles, and then after bubbles, I worked on liquid crystal displays. But like everybody else in San Jose, I got transferred into doing disk drives. I spent a lot of time doing error rate measurements of the component of the magnetic and electronic components in disk drives, and understanding what limited the error rates. During that time, I had met Al Hoagland when he was still in Boulder, and then he and I were both on the local chapter of the IEEE Magnetic Society, so we put on monthly programs of talks, and so I would meet Al regularly, and he kept me kind of vaguely informed about the existence of the RAMAC, and once invited me to listen to the student presentations.
Mm-hmm. Yeah, thanks. So let's talk about then this project and Al Hoagland. So 2001, Al Hoagland, then a professor, Santa Clara University, wants not only to preserve and restore a RAMAC, but also perhaps show it off at a museum, which would take place or be housed in the same place where the RAMAC was developed, which is in downtown San Jose, 99 Notre Dame. So perhaps can each of you also speak to this? Perhaps I'll start with you, Dave, because you were perhaps the one most closely related to the beginning of the project with Al Hoagland.
Well, okay. The machine showed up, and we started out with kind of a rough assessment of it. Of course, everything was.
Sorry, David, but before the machine comes, how did the project start, and how did Hal get in touch with the IBM people, and what was his vision before the RAMAC actually got delivered to San Jose?
Well, it's kind of interesting. In my mind, the idea of restoring a RAMAC began with I carpooled with Lou Stevens, who was actually the second manager in IBM in the development process of RAMAC in the first place, and he and I carpooled together. I live over by the water, and that's where Lou lived, and we started carpooling, and so we talked about RAMAC quite a bit, and the idea came up then that it would be nice to restore one, and Lou always said, well, you'd never be able to get it to work because of those powder clutches, and that turned out to be quite prophetic, but later in dealing with Al was very interested in the collection in San Jose, and he I guess initiated the idea, at least as far as I was concerned, that he'd like to try and get a RAMAC and try to restore it. And I'd been working with Paul Laswitz back in IBM Archives in New York State, and I think at that point I was aware that he had this RAMAC mechanism. It's actually not a complete machine, but it has all the access mechanisms and all the moving parts, and we thought that would be ideal, because it's not really suitable for a static display, but it's wonderful for a display piece that shows the action that's going on, and it has all the working parts of the storage device, which is what we really wanted to do. And so there were various folks involved, but as far as I was concerned, it was Paul Laswitz that made it available, and I don't know who else was working behind the scenes, but anyway, Paul arranged for the shipment, and it showed up in Al Hoagland's office at Santa Clara University.
Thanks, Dave. John, what's your recollection of the genesis of this project and your conversations with Al?
So I had periodic conversations with Al. I knew he was interested in both in doing this, and he was also very interested in trying to recognize the birth of the hard drive at a museum. And his goal at the time was to do this at 99 Notre Dame, a building in downtown San Jose, which there ended up being little plaques and things there. And that building is not occupied right now. It'll probably eventually be torn down and redeveloped. So it didn't quite work out that way, but I think the genesis of that was Al came up, I think probably in his conversations with Dave and the like, of getting the RAMAC to Santa Clara University and starting it as a student project there, which then eventually evolved to it coming to the museum.
Now, at the time you were senior executive at IBM. Did Al come to you for help, and did you help him?
We talked,
pull some strings?
and because I remember meetings with him, but I don't remember any of the details of it, and whether I did anything to help or not, I can't even remember. But I certainly would have been supportive, because the idea of getting one of these devices, both for the historical and just seeing it actually operating, was a pretty exciting concept. Because most of us had only seen it in old videos and never touched one, seen it or anything. So.
And I think for the record, it might be interesting or important to also talk about who Al was and what was his contribution to the RAMAC project of the 50s and the 60s. Yeah. From what I understand, he was still a student at UC Berkeley when RAMAC was being developed.
Correct. So
can you speak to this?
He was a graduate student at UC Berkeley at the time that the RAMAC was being developed. I don't remember all the exact details, but he was involved in the magnetic design of the RAMAC itself, and very heavily designed and joined IBM for subsequent products. And then he stayed with IBM the whole time. And in fact, it's interesting, his so sort of aside a little bit, but he was looking at a technology called perpendicular recording for the subsequent thing to the RAMAC, which didn't end up in products until 2006. So, 50 years later, after the RAMAC. But when I mentioned that Al was my manager when I first switched into hard drive work, and the thing I came into work on was perpendicular recording, working for Al, who had been working on it 50 years earlier.
Right. And so while at Santa Clara University, Al started the IIST.
Correct. So he did a lot of industry education kinds of things. He ran an annual conference that got professionals together, in addition to working with students. And then he also developed this Magnetic Disk Heritage Center and got some funding for that in order to try and preserve the history, and that was the basis for the loan to an organization for the RAMAC.
Right. Okay. Thanks. So then he pulled some strings, get a RAMAC shipped from IBM archives to San Jose, and so then Al is looking for help. Perhaps Patrick, you can then speak to how you got involved in the project.
So I don't remember exactly, excuse me, I don't remember exactly how I first met Al. Excuse me. It may have been through my advisor, but it was an opportunity it was an opportunity for me to spend the summer working on that hardware and kind of learning about it and originally disassembling it.
Yeah, maybe you can speak to some paperwork that I found, a letter from Al Hoagland to, well, I don't have this letter, but it's a letter to some support office in Santa Clara University requesting help to recruit some students in a summer project to help on the RAMAC, and perhaps this is when you got involved. So from what we understand, you started working on this project in June or July
2003.
The RAMAC got delivered in February 2003, so there was a gap of perhaps 5-6 months before you got involved. And perhaps this is where, David, you were there on day first, right? So could you speak to perhaps this 5 or 6 months before Patrick was heavily involved and tell us what happened then?
Okay, well, we started out trying to make an assessment of what we had, and I remember we had to figure out what the electrical connections to the machine were, and so I made a little diagram of what the electrical connections appeared to be into the machine. We noticed right away that it was very dirty, and obviously we wouldn't want to have the discs spin until they were clean, because the possibility of damaging the heads just from having the machine spin was pretty significant. So I think it was at that point, and Jack Grogan was involved, as was I, and he suggested that we get a chemist from IBM to tell us how to clean the discs, and that turned out to be Lou Taft. And Lou came out one day and said, well, what you want to do is you want to use the mildest detergent you can get, and so he suggested Dreft, which was a manual dishwashing soap, and I remember making a wooden paddle for cleaning it, and I don't know when that, apparently, I know that it was Pat that actually did that. I made a wooden paddle and we put some lint-free cloth around it, and he actually applied the soap and cleaned all the disc surfaces, and that was a one-time job. That cleaning job was the last time the discs were ever cleaned. So Pat did his usual good work when that happened. I'm just thinking, what else have we noticed right off the bat? And obviously the air tubing was all bad. It was what they call Tygon tubing, and it was hard. That Tygon hardens up, and the tubing needs to be flexible, particularly the ones that are involved in feeding air to parts that move. And so I got a big package of of tubing for that. Those are the things that I can think of that we did right at that stage. And then as Pat got involved, I would get materials for him as he needed them and that sort of thing.
And I don't know where you sourced them. You were able to find the mating connectors that matched up to the electric interfaces for the
Well, I
RAMAC.
was concerned about that, and that was pretty early. The connectors, I thought, were unique, and I was afraid that we'd have to change the connectors on the machine as well as the ones on the connecting cables. But I found out that those connectors were made by the Continental Connector Company in New Jersey, and they told me that all the connectors on that machine except one were still in production, and they told me the mating connectors, and I was able to go get them. And then the one that was no longer made was similar, and that particular cable had to be changed both sides. But that was a lucky break.
Yeah, so back to you, Pat. Now you're on board. How long did you work on the project, and what did you do?
So I worked on the project for 2 summers. So it was the summer of 2003, and then came back for 2004. 2003, as I recall, was mostly getting the reed arm and carriage all disassembled as far as required, and cleaned, and then verify a lot of the electrical connections. Dave mentioned the Tygon tubing, so we removed the original, which is a series of tubes for the reed heads, but then also the solenoids to lock the arm at a disc and then to lock the arm at a track. So all of that was mapped out, and then using the Tygon and simple cyanoacrylate glue, cut the new tubing to length, and then match up with the existing, how they branched off from a ribbon into each of the solenoids so that it matched. Then put that back together.
That's right. You made a ribbon cable, a ribbon tubing, kind of a.
So that's all super glued together, where you?
It's just super glue. That's all it took.
I wondered how you did that.
Yeah, that was nicely done.
Yeah.
And the tubing is what brings air to the heads to.
Brings to the heads so that they can float on the disc, but it also operates those solenoids to lock the track in position, and to lock the arm especially so that it doesn't wander. And that would crash the discs and be a bit of a problem.
Yeah, there's a total of 5 of these solenoids valves that control the air. There's a detent that goes in a little hole that locks it up down, and there's one air valve that pushes it in and one air valve that pushes it out. And then for the track, there is one that locks it for the odd tracks and one that locks it for the even tracks, and the withdraw is spring loaded, and then there's one that loads the heads.
Did you have an air compressor from the time, or did you use a new one?
Off the shelf.
Off the shelf. Okay.
Yeah, I bought a little air compressor from Sears, and that's what we used in the beginning.
Mm-hmm. It's a good thing it was during the summer. It was pretty loud.
By the way, that's currently in my garage.
And so, speaking of moving parts, which worked first? Did you start spinning the discs, and was it the first thing that worked, or was the head actuation the
I'm not
first
sure.
thing that worked?
Oh no, the first thing was to get the disc to turn, and that's there were 5 wires coming out of that 3-phase motor, and 3 of them were the phase wires. And took a while to figure out what the other 2 wires were, but it turned out it was a thermal element in there, and so we concluded at that point that if we got the phase wires hooked up, we'd just ignore the thermal element, and that's the way it is today. But then using the IBM manual, figured out what it's spelled out what the voltage and current was, and then working with the electrician at Santa Clara University, he got a 3-phase circuit brought into Al's lab with the appropriate current capability, and we made a power cord for it. I guess the electrician made that. I can't remember, but that was the first task to get the disc spinning.
They didn't give us much cable. The disc arrived with maybe 4 inches of wire hanging out the bottom of it. So
Right.
We only had 1 or 2 shots to get that right.
3, yeah, that's right. Yeah, we didn't want to get up into the windings of the motor. That's.
So was everything
I've forgotten that.
shape? Did IBM give you the worst shape RAMAC they had, or was it all dusty and broken, or?
Ask that again.
Well, the state of the RAMAC when you got it, was it full of dust? Was it really in poor shape, or was it one of IBM's worst RAMACs you think you had?
Well, it was pretty clear that it was all there, but as we worked on it, we began to realize that it had been used hard, and to this day we really don't know the history, and that's a lively discussion that we have from time to time. I think the conclusion is that it was either a laboratory experimental device, probably later in the development, but before actual production began, and but whatever it was, or it could have been specially built for field engineer training. But whatever it was, it had a lot of use, and it was worn, and also we discovered from time to time that it had not been properly assembled, and we can talk later about the magnetic clutches, but the clutches had been worked on and put together poorly, which caused some problems later on. In the final attempt to get the machine really running well, but that was beyond the point where Pat was involved.
Okay, thanks. So we have a RAMAC, we have clean disk, we have a spinning stack. Now, Patrick, I saw a little video of you then playing with power supplies and making the heads go up and down and in and out. So could you speak to your first attempts to actually get the head to access the data?
One of the big things we started with was just, again, the disassembly and cleaning of everything, and then measuring all of the taps for the potentiometers to figure out, what resistance readings would tell us the right disk. That was information that we needed to get the arm in the right position. We built a few circuits to actually operate the solenoids, and then there were a few. We started just by moving it by hand and making sure we didn't have interferences, make sure all the bearings were operating properly and that the arm wasn't going to destroy itself. But as far as which one of those went exactly first, I think it was kind of all together, kind of work a little bit on one angle until you ran into a dead end, and then work on another until we had the circuits. And then I don't remember if it was the first summer or the second summer that we put together just a simple microcontroller to start operating the solenoids so that we weren't using switches.
I had seen 2 sets of electronics. There was one that was still around when I joined in 2008 that looked like it was milled out sort of circuit board thing that was the students had used.
That would have been mine.
That you did that, okay. But it looked like there was an earlier version that was done on a perf board kind of thing. So you built that as well. You did both versions, or?
I don't remember who helped me with the perf board.
Okay.
That may have been me that did that. I have to go look at
so you did an early version and then a later version. The later version is what the students ended up using?
Right.
Okay.
Right. There was a prototyping circuit, CNC circuit machine on the same floor as the RAMAC.
Yeah, that's what it looked like it was made.
Using that to make some of the circuit boards. I ended up using that same machine in my design project for building the robots. It was a nice way to get custom circuit boards quickly That was before you could just go on the internet and say, here's my design file, get a beautiful green board back.
So my understanding is that there's only one motor that always spins with gears that make the head go up or down or in and out with just one motor. Could one of you speak to this, how it works, and what did you have to make to actually fix it and make it work? I understand there's some issues. There was some issues with some rubber gears and such. Can one of you speak to this?
I can start speaking to it. There's a motor at the base that's facing up, so a vertical axis, and as it spins, it has a rubber cone. So that cone engages cones on horizontally mounted drums that are the magnetic clutches. And the motor only spins one direction at a constant velocity. That spins the drums in opposite directions. And depending which drum you energize with iron powder inside, that then takes that motion, okay, that's clockwise motion, that drives one direction, or you energize the other for the opposite direction. And depending on which solenoids you have locked, arm versus carriage directs whether that clutch is driving the carriage or the arm. It's actually a fairly elegant system. Very few inputs and motors to get a lot of complicated motion.
And a very clever set of mechanical interlocks on the arm, so it was impossible for it to try and move it up and down while the arm was engaged inside the disc. So it was a fail-safe design. You had to pull the arm all the way out before you could engage the thing that pulled the pin out that allowed it to go up and down. And when you did that, it locked the arm so it wouldn't go in and out. So then the cable that's pulling it will then only move up and down. And then once you lock the pin in, then that frees up the arm. And then if you move the cable, it only moves it in and out. It was incredibly clever, little simple stuff. And the result was the electronics that could drive it, which was all tubes and relays, which unfortunately we don't have. Was very simple, and there was only one set of it that moved both up and down and in and out.
But I know there's a little story about that little rubber cone that you had to kind of...
Oh yeah, that's right. We kind of bypassed that. Actually, that rubber cone was very hard, and it was obviously it would not work and had to be replaced. And again, what do we do about that? Well, I think Jack Grogan again got involved at that point, and because we obviously had to have a new one, and Jack pointed us to a guy by the name of Lynn Liebschutz. And Lynn looked at that and he said, well, the first thing we have to do, we have to get that material. And he said the durometer of that ought to be about the same as you'd find in a hammer that they use in a tire shop. It was about that same. And so I went down and bought a hammer like that and got it to Lynn, and Lynn got a model maker to take that thing and fashion a new, actually it's a rubber tire on a mandrel, and they got the rubber out of the mallet, and the model maker machined a new rubber pinion, which has worked fine.
It's still working today.
And yeah, it's still on there. I have since talked to Lynn, and Lynn tells me that he wouldn't ever want to make it out of that material again because it just made an awful mess. And we thought at one point that we were going to have to do a new one, and Lynn was suggesting alternate materials, but fortunately we haven't had to do that. So that original pinion that Lynn made back in day one has served us well.
Was that also made during that same summer, 2003, when Pat started working on things? or was it before?
I don't.
Or was it done before you were
was
involved?
was that rubber pinion in place when you came on board?
I thought you replaced it afterwards. We had a working pinion when I was there.
Well, that's the only. If you had a working pinion, that's the same one
Then that
we've
must have
had
been.
ever since. There must have been. It must have been we got that done early on.
Cool. Another piece of technology which I found amazing is this powder clutch thing. Can somebody speak of this and describe how it works and how do you got it to work?
John, your
I can
description is
take
good.
a stab at that one. So, magnetic powder clutches are something that are actually still made, even though no one's ever heard of them. There's a company in, I'm going blank, in New York.
Lake Placid.
Lake Placid, yes. Company in Lake Placid, New York makes magnetic powder clutches. Anyway, they're about this big in diameter. You just see the cylindrical housing, and then the face of it is a brass cone that matches the conical shape of this rubber pinion we were just talking about. And inside of it, there's a big electromagnet, and it's filled with iron powder. And then there's a shaft that comes through it, and there's bearings on either side of that so that this thing can rotate without the shaft rotating. And then the shaft is connected to this cup-shaped thing that rides so the edges of the cup go in the poles of the electromagnet. So if the electromagnet is not energized, the powder just bounces around, and there's very little friction between the outer housing and the inner cup that's tied to the shaft. If you energize the electromagnet, then the iron particles tend to all lock up and line up, and then you get high friction between the outer thing moving and the cup shaft, so you generate torque. And it's roughly proportional to the current in the electromagnet, but it's kind of nonlinear, and it's time dependent because they're slow to respond, and it's hysteretics, and meaning it's not the same when you go the current one way versus the other. So they're kind of ugly from a servo control standpoint, but they do work. And they were the same technology that was used to start and stop the reels on the reel-to-reel tapes that you see in all the old movies of old computers, and is also the ones that they have working on the 1401 system also at the Computer History Museum. So in fact, the RAMAC developers had picked these up from the tape guys and just changed the outside of it to match what they needed.
So it's remarkable. That's probably the technology that enabled IBM to show that they could access data with an average access time of less than 1 second or so, to change on a dime and go up and down in a very quick fashion.
Yep. Yeah. It's remarkable because they didn't have small DC brushless motors with modern solid state drives at the time to generate the torques to make this thing move. So they had to generate the torque with an electronic control that was fairly low power, that would then be effectively amplified to generate the large torque, and they could do that through these magnetic powder clutches.
Great. So, all right. So we have spinning disk. We have the head that kind of access in and out and up and down. We haven't talked about the head and whether we're able to fly the head safely over the disk. And when we got the first data read back, who can speak to this?
Well, I read the data back, but before that, Al and his team had actually gotten the heads to fly over the data and to be able to demonstrate that they could read the data back. I'm not sure what they used for oscilloscope electronics and that kind of stuff, but they actually read back and actually wrote to one track of the disk before I ever got involved. And then, so I guess all they had to do is make sure it was clean, and Pat was the one who did that cleaning. So once the system was clean, it was flyable. By modern standards, it was a 1 mil fly height, which by modern standards is very high. And of course, it was all exposed to the outside world. I mean, things were so bad, or so tolerant, that people were allowed to smoke in the presence of the RAMAC. So anyway, so at one point I started to take the head of the arm, and I learned from Al how to move the arm up and down and then lock it into place. And then and before we had the electronic control of the actuator, I moved it by hand from one track to another, and I transferred the data onto a digital oscilloscope, and eventually worked my way through all the data on the disk.
Yeah, so I like fly heights and control of the fly height. And so can you speak a little more about the first time you flew ahead over the disk? Did you have a specification from IBM about the air pressure and the velocities and things like that to make sure
Did you guys get that going first?
Yeah.
The manual speaks to the air pressure, and I frankly don't remember what it was. I think it
was about 55
I think it's
or
about
60
50 psi, but I'm not sure. There's another piece in here, and I don't remember the details because I think Al handled it personally. But he got a team in Building 28 at Connolly Road to do an evaluation of the heads, and we had a number of heads, and they selected that person whose name I can't remember. Selected the best heads that the ones that we ought to use. And there's also the story about the pistons. There are three little pistons. The head actually has three holes on the upper side of it that are 1/16 of an inch in diameter, and there are 6 little tiny holes on the bottom of the head that are air jets that keep the head from actually contacting the disc. So it's a air pressure balancing thing. Well, somebody told us that the pistons ought to be made out of lead, and the folks in Building 28 made us some pistons made out of lead. Well, it turned out that was not the right material, because they worked fine in the first instant, but they quickly stuck to the side of the bore in the head, and so I ended up with an experiment. Well, if they're 1/16 inch diameter, why not try getting a 1/16 inch drill bit and slicing it with a carbide wheel and a Dremel tool? And so I did that, and made some little pistons, 1/4 of an inch long, 1/16 of an inch in diameter, and they worked fine, and they're still there today.
Did any of you witness the first time you were trying to fly the head over the disc and crossing fingers, hoping the disc wouldn't crash?
I think that was the pair of us.
I'm sorry?
I think that was the two of us.
That made those pistons?
I think you made
flew
the pistons.
Flew it the first time.
Flew the first time.
Flew it because we had the manual. We knew what pressure, and we were adjusting it up to that pressure on the compressor. Watching, looking in with a flashlight from the side with the spinning discs. But yeah, we had to take apart it was my recollection that that team gave us more than just 2 heads. We had 3 or 4 of them that we had to choose from, and were able to select what they told us were the right ones. And I thought we also had some of the original pistons, or did we have all replacements?
I can't remember that we had original pistons. We may. Were you involved with the guys in Building 28? Did you come down at the plant site? And
I went
work
down
with
there
them?
once or twice, but more as a visit, not as a there to work. But I remember the
You
lead
remember the
pistons.
names of those guys?
I do not.
Okay.
The lead pistons were. It's almost like they just cut them with some side cutters, and it was pretty clear quickly that wasn't going to work.
So yeah, so you flew the head. I mean, Joe said the fly height was huge compared to today's standard, but it was still small, right? A mil is 25 micron, which is a quarter of the size of your human hair, right? So it's still extremely small.
And Al told me that before my time, the students had actually played around with adjusting the air pressure and seeing how that affected the flying height by looking at the waveform.
I see. Wow. And did you fly the head on a dummy disc or on the actual stack?
On the actual stack.
Actual
We
stack.
didn't have a dummy.
Yeah.
No dummy disc. Okay. Remarkable. So at some point, CHM, Computer History Museum, gets involved. I don't know if I'm messing on the timing here, but at some point the RAMAC ships to the museum here. Who was involved in the discussion between Santa Clara and CHM, and why did that happen? Can anybody?
Al was retiring, and he had to find a home for it. I remember he was having discussions with other places, like he was also considering the Tech Museum in San Jose, and I don't know how he actually ended up here.
Dave, do you remember?
No,
the
I
discussion
don't.
between
I don't
Al and-
remember.
No.
I don't think I was involved in that.
Okay. So, and what state was the RAMAC in when it moved here? Was it about where we just ended the discussion here?
It was
Flying the
before
head?
my time, and before I started doing any work on it at all. It had already found a space in the demonstration lab, which is where the auditorium in CHM is now.
Okay. Do you remember the year?
2005.
2005. Okay. So
I can speak to the condition of the servo and it was the result of the first student class in 2003-2004 academic year. They were able to get both motions, the vertical motion of the carriage from disc to disc, and the horizontal motion of the arm, and they were, and so both motions worked, but it was imprecise, and the servo tended to hunt, and it didn't always go to exactly the intended address, but the motion actually worked, which I think was pretty darn good for senior electrical engineering guys. I mean, that was pretty remarkable. And then the following year, the class was involved in getting the thing to read and write, and they used special tracks on the disc, on one of the discs that were reserved for the customer engineers, so that it did read and write. I don't know, Joe can speak to how well it read and wrote, but the data were all preserved as original, and that's continued to this day. We've never written over the data that were on the file. We don't understand where it all came from, but we haven't changed it, and it's been error-free, and so that's part of the artifact that's been preserved.
Yeah, thanks. So we'll speak to the second stage of this project, which is when the RAMAC comes to CHM. Did I forget anything for the Santa Clara side of the project? Did we
On the
forget anything?
Santa Clara side of the project, so my first summer of 2003, I think was a lot of the mechanical operation. But for my notebook, the second summer is when we really dove into to controlling it, because I had a separate microcontroller, just a very small all-in-one microcontroller with it wasn't a common software. The programming language was a variation of BASIC. But we used that to drive it up and down, and we're selecting disks and tracks. And I know then the first student class or student effort during the year then expounded on that, removed the microcontroller and went to a more standard. I don't remember if it was an Arduino or a different type of controller.
Oh, I thought they were still using the basic stamp the whole time. Did they go switch to something else?
I had thought that they switched to something else.
I have to go look. Yeah.
I developed the basic stamp version, which operated but very slowly, because it was using a ADC to read the potentiometers, and it was just a horrific refresh rate. And the original was all analog. And I think that was where the students were getting into trouble, was that they were trying to be quick, and I think they were trying to rely on the servo to the solenoids to get them in on the track. And
also, Joe, we need to speak some more about your characterization you did on the disk and all the read-write experiments. Was this done mostly at Santa Clara or mostly
It was all done here.
Down here, okay.
Yeah, so we collected the waveforms, and with the waveforms, we could do a lot of the analysis of how well it worked as a recording system, and we found that it was very robust compared to modern disk drives. The raw error rate, it's hard to actually determine an error rate, but because we only have a few thousand bits at a time to use to make extrapolations, and the calculated error rate is like 10 to the minus 40th. So when you're extrapolating that far, there might be some errors in the extrapolation too. We found that so if you believe that error rate, then you should never encounter an error in the whole life of the universe. The other thing we found is one of the ways we characterize modern disk drives is this parameter that we call KUV over KT, which basically tells you how much energy is stored in one bit. And so if you know how much energy is stored in one bit, you know what the likelihood is of it being flipped over thermally. And in a modern disk drive, John might know this better, but I think the typical number for KUV over KT is around 80 to 100.
If that.
If that. Well, it was over 240 on the one disk we tested, and since the 240 goes in the exponent compared to the 80 to 100, that means also that statistically there's no chance that in the life of the universe that a bit would ever flip, at least at room temperature. So the basic system, let's see what else. We had one of the disks analyzed by some friends at COMAG, and they took the disks and they did some microphotography of the disks, and we found that, not surprisingly, the disks were randomly oriented particles of iron oxide. By the time you got to the later versions of iron oxide, they were long, narrow needles that were all oriented. And so on our disk, the measured coercivity was about 260 Oersteds. By orienting it, you increase the coercivity, and it's, I think, about 350 Oersteds in typical later disk drives, and also a better signal-to-noise ratio. So, but still, we had a signal-to-noise ratio of about 32 dB on this, which, if you look at the waveforms, you can see it's very clean. It's very easy to see where the pulses are and be able to make sure that you are detecting the pulses reliably. Modern disk drives, the signal-to-noise ratio, I think, is about 20 dB. And so, but they also survive with raw error rates of about 10 to the minus 4. And like I said, our raw error rate, we believe, is 10 to the minus 40th or so.
Thanks, Joe. So, all right, so at some point, the RAMAC comes to the Computer History Museum. Al retires. So I'd like to kind of understand who then takes control of the project. Was Al still in charge and dictating the shots, calling the shots, or did somebody else take the ownership of the project? Who could speak to this?
Al actually had an office over here in the administrative area, and I don't know exactly what his schedule was, but he was always here when I was here, and I basically came in about once a week.
Okay. All right, and then so no more students, or were you still involved, Patrick?
I stopped by once or twice to meet Joe and a couple other things, but I didn't do a whole lot of work here. At that point, I was hands off.
Okay. And John, is this about when you started to be involved?
No, it was a little bit later. So, because Dick Oswald was brought in before I was involved. So, if it came here in 2005, I started in mid 2008 after I retired.
And so, what type of work went on between 05 and 08 then here? Who can speak to
I
this?
was collecting data.
Okay, all right. So let's go back to you then.
And that was the principal work that was done at that time. It was Joe getting all that data, and we'd have regular meetings where we'd talk about where we were going. Dick Oswald basically, he wanted to try to follow the original design, basically using modern electronics, but to follow the design concepts that were used in RAMAC with the vacuum tube and relay approach to things, and he was collecting pieces to put that scheme together, and that went fairly slowly because Dick Oswald was doing consulting work for another company, and it was taking a lot of his time. And I think that Al Hoagland became concerned that the project wasn't progressing as fast as he had in mind, and so he brought John into the picture, and for a while there were the two parallel efforts. I think at least in Dick didn't know what John was doing, and John was starting in on his approach, and so I brought Dick back into the picture because I thought that at least there ought to be a meeting of the minds and not have two separate versions of the thing going on.
By the way, a question that I forgot to ask is manuals and all the documentation from IBM. Did we have all the documentation from IBM?
Oh yeah,
then?
that was actually, that really goes back to the very beginning. That was the source of data, and there basically were two manuals. One was the maintenance manual. I've forgotten what they called it, but the other was the instruction manual, and they had kind of different approaches. And a lot of the same material, but between the two of them, it was a pretty good. Although Pat was amazing, because he basically was able to take the material from the manual and actually put it together like it was instructions on an erector set or something. But the manuals weren't that precise. But Pat was able to read between the lines, and I'm not aware of he ever put anything together wrong. It just, a lot of what he did is the way it is now. We've never touched quite a bit of it.
You should try reading a mid-90s Tamiya remote control car manual.
Well, okay, well that's
IBM manual was
that's
actually
your training,
very well written in
But
comparison.
anyway, you did it very well. But anyway, yeah, that was the basic set of knowledge that we began with, and we were lucky that was available. I don't know how we ever would have gotten this job done if we hadn't had that information.
All right, so let's go back to you then, 2005 to 2008. Joe, how did you get to
So we
do all this?
It was done in the laboratory downstairs, which is no longer there, but it was in a glass computer room that was right off the lobby, because that's where companies like to show off their computers, right? So that was what the museum used for a demonstration lab, and so that's where I was working 3 or 4 hours a week to collect data. And at one time, our goal was to be ready for the 50th anniversary celebration of the RAMAC, and we were going to have. You remember that, Dave? We were going
Forgotten about the goal. Yeah. Yeah.
And we were gonna. There was going to be, all kinds of
September 13, 2002. No?
No, not 2002.
Commemorative event where?
It would have been 2007. 6 or 7,
all right,
yeah.
Never mind.
Yeah, it would have been 2006 or 7. And what I remember about that was that originally the museum had planned to do it as exhibiting one of the artifacts of the museum, and somehow IBM found out about it and said, "Oh, let's have a much bigger celebration." And then I don't know exactly what happened, except a lot of money got poured into it. It got to be a very big event. One of the things I remember is that my job there was to run the RAMAC and show off waveforms, and so we borrowed an oscilloscope that we could project onto a screen, and so people could see waveforms live. And one of the memorable things from my point of view was Jack Harker was one of our visitors, and he came by and he said, "I remember the waveforms used to be a lot less noisy." And I said, "Yes, but I have a 500 megahertz oscilloscope." And he was satisfied with that answer, because his oscilloscopes, I think, were probably either 2 or 5 megahertz at the time.
So for reference, Jack Harker was one of the original engineers on a lot of the mechanical pieces of the drive, and he was fresh out of school at Berkeley at the time he was working on it. And when I started in the company, he was a senior executive over development kinds of things. So,
just to set the stage, Joe, could you kind of remind us of the aerial density of the RAMAC compared to standard disk drive today?
Let's see. It was 100 TPI. No, 20 TPI. 20 TPI.
Track per inch.
20 tracks per inch, and
that's in the cross-track direction.
cross-track direction, and must have been about 1,000 BPI.
100.
100?
It's
Wow.
like 100.
100 bits per inch in the
Yeah. In the longitude at the ID. So about half that at the OD then.
Okay, so 20 and 100. Yeah.
This is
Yeah.
2,000.
2,000 bits per square
So-
inch.
So it stores 5 million customer characters, and the characters were 6 bits, as we like to remind our visitors all the time. It's not an 8-bit character, it's a 6-bit character, because they were mapping a holorith card onto the RAMAC, and a holorith card only needs 48 characters.
Yeah, so I don't know, in relative terms, if the size of a bit today was a penny, then the size of a bit of the RAMAC would be the size of Central Park or something, something like that.
Let's see, I don't know. We talk in terms of terabits per square inch now, right? Gigabits per square inch. I don't know. I'm losing
Terabit
track.
per square inch today, 1 point
If you go 2
something.
terabits and 2 kilobits per square inch.
Right. So
Tera is trillions, so
10 to the 9.
2 to the 12th divided by 10 to the 9th. So it's a billion times more dense now.
billion times more, yeah. It's quite amazing, yeah. So that just to sets the. But so who got the idea to, which was fairly ambitious, right, to read all of the data, even though it's fairly small data set compared to today's disk drive. It was still a lot of work for you. So could you speak to this?
Well, you know, I just started doing it and systematically, one disk at a time, and when I got to about 20% of the way through, I said, you might as well just do the whole thing. And there wasn't any other competing activity for time on the RAMAC anyway. So
how long did it take you?
more than a year. I don't, you know, I'd have to go back and look,
More
but
than a year.
well over a year.
How many hours per week in average?
I would say it was about 2 or 3 hours per week, and I would get both surfaces of the disk done in that time.
And so you got the waveforms, you still needed to decode this into characters. How did that work?
Well, so I wrote some code that would do what I remembered a peak detector does, which is that you ignore everything below about 50% of the peak, and then you fit a parabola through the peak and calculate where the peak of the parabola is, and that's the location of the peak, and then you just say those are the clock positions, and then you say, okay, well, if you know the clock positions, you've basically got it decoded. You just have to put it into a table. And the only thing that we originally found mystifying is that after I got my code debugged and working what I thought was properly, the data still didn't make sense, but it almost made sense. And then I realized that the data was coming out backwards.
Or
And
the disk spinning in the wrong direction? Or?
yeah. So it turns out that Jack Harker, I think, is the one who told us that the reason they did that deliberately was because when you do arithmetic, you do arithmetic from the least significant character first. And so that just made it easier to do the arithmetic in the machine.
And that was not in the manuals?
I don't know.
I think it was all there.
It was?
Yeah, I think so.
Okay. I remember mentioning it to Al when I figured that out. And Al didn't volunteer a solution to that either.
So you coded all this in some language?
Oh, I coded it in Turbo Pascal. So the only trick was that it was that the data came in 10 megabyte bunches for 2 revolutions around the disk, and Turbo Pascal has trouble handling more than 64 kilobytes at a time, so I just had to do some dirty programming tricks to take care of that.
Okay, so at some point you have characters, you actually have the record of what's on the disk. Could you speak to this?
Well, I'm of the opinion that that it was probably stuff that the student customer engineers did as part of their exercises of learning how to do the machine, because there is not enough data there of any one type, I think, to be meaningful for a business. I mean, there's some that looks like it might be the records of an insurance office in Canada, but not enough of that data to be enough clients for an insurance company. And then there's some companies that also Canadian, where you can recognize them, like Canadian Tire is there, and London Drugs. There's a section where there's a lot of different car brands,
Car models, yeah.
that you wouldn't exist anymore. I mean, there was like Vauxhall and Morris Minor, and I don't remember all of them, but they would have been the ones you would have known from the early '60s.
Now you mentioned that there was also mention of the World Series of 1965 or something. Could you speak to this?
Oh, so there's a clear reference to Sandy Koufax being named as the most valuable player in the World Series. Now, we can't tell whether, since he won it twice in '61 and '63, we don't know which year that was. But that means that the data is at least that recent. If you go farther on, there's some data that refers to Expo '67, but that might be, forward-looking stuff having to do with the organizing committee or something like that.
Mm-hmm. Mm-hmm. So, what's 5 million characters? Is that a book? Is that a chapter of a book?
I don't know. 100,000 words is a novel. So that's what.
Okay.
So,
Curious, yeah.
So 100,000 words and 10. When I learned typing, it was 5 characters per word. I think words are actually longer than that. But
So that'd be like 10 books.
okay.
Yeah.
But I guess
John can do math. He's younger than I am.
at that time, companies were happy with that much storage, and they could do airline reservations and checkbook management and all that stuff, right?
Yeah, I don't think they had real-time operating systems for that. I mean, when I went to school, I remember disk drives were available to speed up your calculations for data that you had on tape, and when you submitted your deck and your tape reel, you got allocated a certain part of the disk drive for running your program. When your program was done, you were gone. You weren't on the computer anymore.
I know we spoke a few months ago about the Olympics in Squaw Valley. That first Olympics to use.
Yeah, they were using it for keeping track of scores and results and all those kinds of things. There's a whole advertising brochure describing that IBM put out.
The RAMAC in Squaw Valley.
Yeah,
it's pretty cool. Yeah, and John, I think you mentioned United Airlines.
They bought
recently.
2 of the first production units and put it into their airline reservation system. This preceded the larger IBM American Airlines thing that developed Sabre on a couple generations later. But yeah, they had built it in and put it in. Looks like they put it into production. We have copies of employee magazine from United Airlines in '58, I think it was. I forget which year it was.
And the first customer for RAMAC was a paper company in San Francisco?
That was the prototype. There were 14 prototypes built basically in the year before the production began, and the first one went to Crown Zellerbach Paper Company in San Francisco, and I guess for inventory control. I never heard much about the application, but all of those 14 machines were recalled systems. They were systems, and the drives were quite different in configuration. Fundamentally, they were the same, but the systems were recalled because they had reliability problems. They depended too heavily on relays, and so the customer uptime was not acceptable, and so all 14 systems were restored, recalled, and one of them exists today, and that's the one that's at Almaden Lab. It's the only one left in the world.
All right, so thanks, Joe. Now comes John, and your part of your involvement in the project. Could you speak to this and what you did?
So Al and I talked, and I don't remember whether he initiated it or we had been just keeping track of what was going on in the RAMAC anyway, because I had been interested in it and had, like Joe, had gone to one of the student presentations a couple of years earlier. So anyway, after I retired in 2008, Al and I met at the Saratoga Library, I remember. We met a couple times and discussed what needed to be done and everything. And I said, sounds like a fun project to work on. I said my only criteria was I wouldn't work on any politics related to internal things with companies or museums or whatever. I just want to work on the RAMAC, and he said fine. Then I got, and Al and I had talked about the architecture for the thing. Dick had made pretty good progress. Dick Oswald had made pretty good progress on the design of a very different approach than Pat and the students had taken to the thing, which was emulating, but with modern solid-state electronics, the basic operation of how the original RAMAC worked in terms of using there was a bunch of taps on the potentiometers that were used for measuring position and doing an analog servo. And Al and I had both talked, and Dave told you that was going a little bit slowly. And Al and I had talked, and we kind of agreed on the philosophy. We'd like to take the other approach, which was, if you're not going to restore the original tubes and relay stuff that we didn't have, just go completely modern with a modern microprocessor and switching drivers and those kinds of things. Through sort of hobby projects and things for ham radio and high school robotics, I thought I could do it, even though it's like nothing I'd ever done in my career before. So then I started designing a controller around this, and use a different kinds of transistors than they use that would drive it a little harder, and a little bigger microprocessor that was faster, but it was basically the same concept as what the Santa Clara students were doing. And built a little controller for that. Then Dave got Dick and I talking together, and I think I convinced Dick that it wasn't crazy what I was going to do, and that I sort of knew what I was doing, and got a lot of advice from him on how to do the servo properly, which was very helpful. And then all the power supplies for it, Dick actually built. So the ones that are currently being used, Dick built the power supplies, and I built the microprocessor and other interface controls for the thing. And then at the time, it was, I think, which Joe was describing where we were in this sort of glass-fronted room that no longer exists at the first floor of the museum, and that's where things were. And so we would come in and meet once a week. And I don't know whether you were doing that beforehand. We'd meet once a week on Wednesdays, and I don't know whether that once a week on Wednesdays was started before I was involved or just after I was involved, but it was a great time because that was the same time as the 1401 restoration team was in. And they were just fun people to be around. And they didn't like rules or anything else. They were just, so we enjoyed talking with them, and they were very helpful as well on things. When we get to the clutch restoration, Alan Palmer had done the clutch restoration along with Grant Severe's for the tape drives, and so they were very helpful. And Ed Thalen, who was also, it looks like he had been coming to meetings for some time, because I see on his website he has records of things. So he was helping document what we were doing. So anyway, it worked, and he was heavily involved in 1401. So it was really good to be at the museum at the same time they were.
And was Al still very much involved?
Al was, I'd say, he wouldn't be there every week and every meeting, but we talked to him quite often. But as time went on, it would fade to less often, because he was starting to spend more and more time, I think, with his daughter in Oregon. I don't remember the whole story, but he was spending less time.
Well, he moved there somewhere, somewhere along the line, and then he very irregularly would come down to visit, but he was not a regular attendee in the weekly meetings.
Right. And then I thought, well, we're going to do this whole servo system with modern control theory that I kind of, sort of, but don't really know how to do, but it'd be a good education anyway. So you got to have a good model of the system. So, well, we'll measure the torque of these powder clutches versus current and things, and turns out you can't do that when they're not spinning, because it's got to be spinning to have the little powder moving around for it to be consistent. So I tried to do that on a bench. It was totally inconsistent. I don't know whether you guys ever tried to measure the clutch torque or not.
I measured what it took to start grabbing.
Okay.
As referencing my notes during break, I could see that I wasn't just using them as an on-off. I was using some amount of proportional.
Yeah, so I was trying to get the whole proportion of the constants and everything. And later on, Dick actually had a good way to do it, which was he had a strain gauge you could put while on the RAMAC when it was spinning and measure. Then we got characterized, but this was after we had it working, basically. But anyway, so I tried to characterize it, model the whole thing, and was never terribly satisfactory. But in the end, I decided I'll just sort of emulate in digital the actual control algorithm that the original guys used, because we had their original paper on how they did the analog control for it, and I did that, and it mostly worked. But we had the clutches. One clutch was kind of working, one wasn't really working very well. They were not consistent. So that's when we realized we probably had to refurbish the clutches, which was that, and the cable that moves it up and down was also frayed, which I guess you didn't replace the cable, right? Yeah. So those were the two major remaining refurbishment things we did. So when we took the whole clutch with the two clutches and the shaft and everything at the bottom that drives the capstan that has the cable wrapped around it, when we took that apart, the bearings were kind of frozen to the shaft. The shaft was scored. It looks like the bearings had frozen up and rotated the shaft, so that the shaft was a complete mess. And that's where Dave came in from his old car stuff, because he knew some guy, he can fix this shaft, so you can tell that story.
Well, he was an old car, a friend of mine. He had a business in Southern California. He called it electronic chrome and grinding, and he had two major customers. the drill bit world for oil drilling. The process was that he would plate hard chrome on a damaged shaft, and then he would centerless grind it back to size. And that was exactly the problem that we had. We had a shaft that was badly scored or fretted underneath this frozen bearing inside of one of the clutches, and that shaft and the clutch was basically unstable on the shaft, and so that the performance of the clutch was inconsistent. And by getting that shaft hard chrome plated and ground back to its original size, the shaft was essentially restored to being as good as new. But that was actually the final fix that made the thing work. But we had other stumbles along the way, and one that occurs to me is that one of the air solenoids started leaking and misbehaving, and that was because the plunger in the air solenoid actually had a seat for the air valve inside the plunger, and trying to replace that plunger would be enormously difficult. And again, we lucked out, because the company that made that air solenoid was called Skinner, and I think they sold out to a company that again sold out to a company called Parker Hannifin. And I lucked out one day. I was trying to research where that thing came from, and I ended up talking to a guy at Parker Hannifin who'd been there for years, and he said, "Oh, I can take that IBM part number and let me do a little research on it." And he came back and said, "Well, you know, we have a repair kit for that solenoid. It's not the same as your solenoid, but it uses the same plunger, and we have a repair kit for it. And I think if you go to a jobber somewhere, he had a jobber that he thought might have one of the kits, and he said, if you might be able to get one from him, and then I'll see if I can get some more kits made so that you'll have some spares." And so, boom, that problem was solved. That was one that could really have bothered us. I guess in retrospect, we could have used the solenoid that loads the heads, because we've never actually had to load the heads in the museum, but be ashamed to rob Peter to pay Paul, and the fact that we could get those kits was a huge help. And so again, we stumbled into a solution.
Thanks. Yeah, so back to you, John. So at some point, you hear from DAG or from CHM that this RAMAC will go into the exhibit, the Revolution exhibit.
Right.
And so did you have like a hard deadline?
At that point, there became a hard deadline, because they started the construction of the exhibit. In fact, at that point, we lost the location we were at in the museum, because that got torn down. And then where the 1401 room is now, the 1401 room was smaller, and they had a shop to the left of the entrance to the 1401 room, and that's where we were doing the work, sort of at this time frame. And yes, so the museum, we had to have it done by the end of 2010, or it was too late. So I'm trying to think of which. I could probably dig up the exact date, but so we had to refurbish these clutches. We had to get the bearings out, and they were stuck. And Grant Severe's, who had helped refurbish the clutches for the tape drives, he had this wonderful shop that was in like a warehouse building up on Mount Hamilton Road. This was all before he moved up to the Pacific Northwest. And so Dave and Ed Thalen and I went up to his shop one day with the clutches, and we took them apart and got the bearings out that were all frozen. I had identified a source of the bearings because, like the ones Dave described earlier, they were all standard bearings that you still made today. We found that there were felt seals that prevented the powder from getting out through the bearings. On one of the clutches, the felt seals were completely missing, which was probably why the bearing failed. Grant had felt and made new seals right there while we were in the shop that day. So we had a good day and basically got all the pieces refurbished, and then we brought the clutches back down in the museum. Grant had identified the company that still made the magnetic powder, and so we had that, and we carefully weighed it because we knew how much was supposed to go in, and put the powder in the two clutches, reassembled them. By that time, the shaft that David had refurbished was back, assembled the whole thing, put it in. Then the cable was frayed. That was another Dave sourcing story. I don't know where you found that cable source.
Yeah, well, a couple of things come up there. To get back to the clutch versus shaft thing, it seems to me that we put the thing all together and we were trying to avoid having to do something about the shaft, and we put the whole thing back together with the refurbished clutches, but it was still inconsistent, and we came to the conclusion that we'd have to do something.
Oh, that's right. I forgot we put it back together before we refurbished the clutch.
I think so.
Yeah, you're
and
right.
So I think the piece that determined our meeting the schedule was the guys that were redoing the shaft, and they turned that thing around in something like 2 weeks, which, that was a busy shop, and they had a lot of business. And so, my old car friend, I guess, really made that happen in a hurry, and that was a boon to our. And we really met the schedule in the nick of time. As far as the cables go, that was we got a sample of it was a very flexible 1/16 of an inch diameter wire rope, but it is made of very, very fine strands of material, and they wanted us to buy some horrendous amount, and all we needed was a few feet, and so eventually they agreed to give it to us as a sample. I don't think we paid anything for it, but I prepared a couple of the ends were taper pins, and then there was one end that John made on his he had a fancy little milling machine, and he made that piece, and but all the ends weren't much bigger than 1/16 of an inch in cross section, and I had to put the cable into a hole that wouldn't break out of that. That was the first problem, is getting the hole centered on the little fine taper pin, I think, in a couple of those conditions. But the real problem occurred the day that I started to put that thing together, and I found that when I went to cut the cable, and I used a carbide wheel and a Dremel tool, as soon as I cut it, it started unraveling. And holy smoke! How am I gonna get that unraveled cable into that hole, and how is that gonna work? And so the first thing I did was jam the unraveling ends into into a vise so that it would stop unraveling. And I thought, oh God. And then it occurred to me, well, if I was going to silver solder the cable into the end pieces, and I thought, well, maybe if I put a little spot of silver solder at the point where I'm going to cut the cable, before I cut it, I can cut it and it won't want to unravel anymore. And that turned out to be the magic that made that work. And after I put the silver solder on it and cut it with a Dremel tool, then I could actually taper the end on a grinder and stuff it in the 1/16 inch hole, and then heat the thing up and reflow the silver solder, and that worked out fine. But boy, I went through a what in the heck am I going to do now kind of experience.
Yeah, so there were all these mechanical fixes at the last minute, but then in the
then,
meantime you were developing the software. And,
so I'm working on the software. Of course, I'm panicked about breaking the thing because servo goes out of control. It goes whack, and I mean, so I modeled everything and made sure it wouldn't go out of control. Anyway, I spent a lot of time at that and got it so I think it only banged the in out once. Kind of hard, but every other time it was always kept within control. So I got the in-out working very well and going from track to track and doing what it's supposed to do at roughly the speed that it's the original was. But I was terrified of doing the up-down because it's a lot more motion there. And I don't know whether you were braver than I was, Pat. But anyway, so there was a point where the museum wanted to actually get some videos of the artifacts and things, and so they brought a whole film crew in to do the RAMAC, but it was only going in and out at the time, so they didn't get the whole motion, unfortunately. But then later I started working on the up and down. We were running out of time, so instead of coming in an hour a week, I was coming in every day for many hours until it was finally working well until. Then Jack Harker came by one day and to talk to us because we got it working and we wanted to show him it working and it's moving. He says, it's moving too slow. It ran much faster than that. So
were you above the 1 second?
Yeah, it was
threshold?
well over. It's probably closer to 2 seconds at that point in time. So he said, it was way too slow. So I worked on it for another week or two, and we brought him back, and he said, that's much better. So it was a lot faster then. So it was up to what it is now, which is now actually still probably slightly slower than the original was. But got it all working, and then...
could you speak to what Mason did, the late Mason Williams?
Yes, that was a huge piece of it. So early on, right after I came on, I realized, so I was going to work on this microprocessor thing that was just going to do the controls, but it's not going to be very good for telling it to do a whole sequence of things or doing a demonstration or everything. And Mason, I had known for many, many years. Actually, he was my next boss after Al at IBM. It's another story. And Mason was this brilliant guy. He was the only person I knew that 20 years after taking it in school could still do contour integrals. But anyway,
another Caltech.
Yeah, he actually was also a Caltech guy. He was 10 years ahead of me and 5 years ahead of Joe or something. Yeah. So anyway, Mason also was good at writing PC programs and GUI stuff and everything, and I knew that because he'd done a lot of things on it. So I thought Mason loved history of things. So Mason, would you like to come work on this? Yeah, sure. So he wrote the program that we use today that runs on the laptop that tells the controller I did what to do. But also when it tells it what to do, he built a complete model of the whole thing that displays it running graphically for every command that he gives it. So you can see it doing it as it does it. And because we didn't want to load the heads to read the data every time we go to a location, because if the little holes that form the air bearing ever got clogged, then the head crashed, it would destroy the entire thing. We don't load the heads to read, but we wanted to show what the data looks like at every location. So Mason's program also takes all the files that Joe had captured years earlier, and it's sitting on the same laptop, and then as it goes to a location, it displays the actual waveform for that location, decodes the data and shows what the decoded data is. So he did all of that. It was a complete model of the thing, and really nice to be something that's good to demonstrate.
It's a great feature at the demo, right?
Yeah, so it was the thing that made the demo decent, and none of the rest of us could have done that. That was all Mason.
And I wanted to say that Mason's control is not just an animation of what he intends to have the RAMAC do, but it actually models it so that if you look closely enough at it when it's moving up and down, you can see some servo issues, like there's overshoot in one direction and there's a little undershoot in another direction. Mason's model actually includes that.
He built all the physics of the behavior into this program. It's not just for show. It was very complete job.
So at the end you claim victory.
So we claim victory, and at least the date on the photos that I have of the day we wheeled it into the place where it is now was November 30th, 2010.
And then Revolution opens up January 11 or something?
Yeah.
And you guys do demos?
An hour a week on Wednesdays. It's still on Wednesdays. It's still the day the 1401 guys come in.
Since 2011, so now 13 years and counting, yeah?
Yeah.
Okay. And
except for the 2 years for COVID.
Yep. And I know my thought originally was we'd be lucky if this thing would work for 5 years and we'd be maintaining it. It'd be horrible to maintain and everything else, but we'll get a few years out of it. And now I think we put a few drops of oil on it once every 3 months, and it just works.
And it keeps going and going.
Yeah, it's an amazing machine.
Right. So who wants to talk about who shows up at the demos? What type of feedback you get?
We've all been through that.
We've already mentioned Jack Harker a couple of times. He's made a lot of visits.
How many people show up?
In terms of visitors, we get anywhere from a small handful to 50 or 60, depending upon, and it's Wednesdays on the weekday, which isn't probably the most popular day for the museum, but we get sometimes a pretty good crowd. And they're from all over the world. And some of them have engineering backgrounds, some of them don't, some of them are young kids. I got very excited one year. There was a 10-year-old kid that sees the thing and says, "Oh, is that cable, serial port RS-232 over to the thing, and can I help start it up and run it?" And the kid asked incredibly detailed questions about how everything worked. I don't think he was more than 10 years old. So we get that kind, and
You get people asking, what's a disk drive?
We get people asking what's a disk drive, but most of them do. But we also get disk drive engineers, and some. We'll take a crowd, and the difficulty as we do the presentation is assessing that level of detail that these people are interested in, and some will drill down to the details of the magnetic powder clutches, and some just are sort of interested in the overall high level thing. So, but it makes it fun.
And these people from all over the world, right? Yeah.
All over the world.
Yeah.
And Bruno, of course, you're one of the key demonstrators these days as well.
When we do oral history, Computer History Museum likes us to ask a couple of questions. What's the proudest achievement that you think you've done in this project? Have you guys? Do you want to give it a crack at that? Start with you, Joe. What's your proudest thing?
I'll pass. I mean, it's just a lot of stuff to get done. It's been a lot of fun.
sometimes it's just the interaction with the visitors of the museum, which in the end was the goal. Other times it's the specific technical problems we had to solve. The biggest thrill was one of the early days when we got it really working, and seeing this thing come to life. Actually, the day Jack Harker came in and saw it and started talking to us, that was a big thrill.
Dave, any?
Well, I don't think I have anything specific. It's just that looking back on the whole experience from when the thing first showed up until the day that we got it on display downstairs, and then every week to do the demo. I mean, it's just in my view, it's the satisfaction of everything from, what are we going to do with this thing? How are we going to make it work? And then working with Pat and the students in the early days, and then basically John came on and we started from scratch again and went through as it started working better and better, why we peel a layer off the onion and there's another task inside. I mean, it's just been a nice time.
Mm-hmm. Patrick?
For my 2 summers worth of working with it, it was nice to be able to take something that wasn't working, had a not thick layer, but decent layer of dust on it, and get it cleaned up and actually see it start moving again, and build some interesting control work for me kind of on the side, and really a nice way to kind of branch away from mechanical engineering into other fields, and it's kind of served me well.
To this day, I'm amazed at how much you got done in that summer. It was a phenomenal accomplishment.
Yeah.
Well, we still appreciate the craftsmanship of what Patrick did too.
It's all held up. I mean,
Just curious, Patrick, when you were looking for a job after your Santa Clara stint, did employers, when you interviewed, did they ask you about the project?
No, that didn't come up, to be honest.
Okay. The other question is, if you were to do it all over again, would you do it differently, or Joe, is there something you would have done differently?
Well, the only thing I wish that I could have done at the time was to automate the whole data collection process. Now we have everything in place that it could be done, but we're not motivated to do that anymore.
I still don't know how you had the patience to position that thing over 10,000 different locations and do it. I don't know. Every bit of it has been enormously both satisfying and a lot of fun, and mostly just working with the people. It's been great. So I'm not sure I'd change much at all.
Mm-hmm. David?
Well, I've been involved in a couple of other restoration projects, and it's kind of the way it works. You basically, sooner or later, you end up looking at every piece and figuring out what you need to do to that piece in order to make it function the way it originally did. And in some cases, you find out that you have to make it function better than it originally did because the original function of it wasn't that great, as in the case of some of the cars that I work on. But in this case, the RAMAC is quite an amazing machine in that here we have a group of young engineers that were brought into their first work situation, and they came up with a product that's very complicated, but the amazing thing about it is when you get it back to the way that it was originally put together, it's amazingly reliable. It's really a a beautiful piece of work that involved 40 or 50 young guys working together that was well done, and so well done that it was the foundation of an industry.
Patrick, if you were to do it again, would you do things differently?
I think if I were to do it again, I'd probably stay more involved for longer.
You're welcome now.
Yeah, you missed a good bit of the fun.
You got to work
clearly.
on JWST though.
Okay, well, I have a last section, which is what I'm going to do next. It'd be fun to talk about that, but before I do, did I forget anything? Is something that you guys think we should mention?
As soon as we go out of this room, we will think of 10 things.
Nothing that comes up now, okay. So, all right, so what's next? So on my list of questions, possible new project, would you guys be interested in restoring the electronics? If you had the other half of the RAMAC,
Absolutely.
the tubes and relays, would you be interested in doing this?
Yes. I'd say the probability of success is probably marginal, even if we had it, but yeah, it would be fun to do.
But we know what needs to be done now. I mean,
We do.
So and at least we remember enough about vacuum tubes that
Yeah.
that there's a chance that we could actually make it work.
Okay. Would you entertain doing read-write demos on this RAMAC?
Museum
right now,
won't
you
allow
try
it.
not to read, you don't even write.
I would say no. Wouldn't risk it.
You wouldn't risk it. Joe?
The students already demonstrated that it could be done, and I don't think we need to do it again. I mean, there's no mysteries in doing magnetic recording in this environment.
Okay. Do you guys have different opinions, Patrick? Do you think you should spur this guy? And
No, I don't think I would
No.
change from what they have said.
Dave, do you think this is a reasonable?
Oh yeah, I think where it is where it ought to be.
Okay, all right. Would you guys entertain doing weekend demos or going into twice a week demos if there seems to be a lot of demand, right?
I think instead, separate from this, we need to be able to recruit more people on the team so that we can have better burden sharing in that case.
Yeah, I agree. I think we should do it. But
Yeah, you think
we just haven't, we've talked about it multiple times
Right.
over the last
think weekends
year,
could be
but we
a-
just haven't done it because
Right.
we weren't motivated to give up the weekend
Right.
yet. So
Does would CHM like to have weekend demos?
Yeah, I think that
Yeah.
the 1401 guys have better attendance on their weekend demos than they do on the weekdays. It's just that I don't know that any of us want to start doing weekends.
Would any other, so there's 7 or 8 other RAMACs that we know of in the world, right? Most of them IBM owned. But did any of the owners come to you and say, hey, I'd like to emulate what you guys did on your RAMAC to get my RAMAC up and working? Did that ever come up?
No.
No. How
No.
difficult would it be if they come to you and with
There
that
is the
request?
there is the one machine that exists that's in being stored at the Connolly Road plant site that belongs to Western Digital, and if that were available, that has the original electronics, and I think there's a case to be made for restoring that if it ever became available to us.
Yeah, I think we would need about 500 to 1,000 square feet of laboratory space and probably a commitment of 2 to 5 years to have that space available.
For the electronics.
to work
Right.
on that whole system.
Right. Yeah, no, I agree.
Plus, if the electronics, some of the maybe that's what you're referring to. The electronics, the vacuum tubes or whatever is involved. If the pieces could be, if it's functional, that's one thing. If they need to be reproduced, that it could balloon out of the state of possibility pretty quickly.
Yeah, I seem to recall that most of the tubes were 6AS7s or the equivalent, and they are not that hard to find.
I think the museum has quite a few of those. The museum has a huge collection of vacuum tubes. It just may not be the ones that we would need.
How about a 1301? I think CHM has a 1301. So the 1301 is the successor to the RAMAC, or one of the successors, but the first one to use solid state and multiple arms, self-acting air bearings. Would that be a fun project to undertake?
The 1301 that the museum has came from the collection at Connolly Road, and it's in poor mechanical condition. In fact, when it was still at Connolly Road, I had to put a wooden block in there to bring the mechanism up to where it looked like it did originally, and I can't remember what was missing. Oh, I know. Part of it was the shock mounts for the actuator, but I think the actuator itself is in poor condition. So I think it would be very challenging, and none of that's impossible. But again, like any restoration project, you get into it and then you find out it's a much bigger deal than what you thought.
John, is that something you would be interested in doing?
That particular one?
1301, yeah.
If there was a good enough team, I'd be interested in being involved. For just us to do it or something, probably not too much.
Okay. So unless I forgot something, this concludes our oral history interview. So on behalf of the museum, I really want to thank you for this. I know it's been a long time in the making, but we actually did it. And so I really just want to thank you very much for your time and your cooperation.
Great.
Thanks.
Thank you very much.
Thanks very much, Bruno.
It's been a nice time.